Okay, what is a logarithm?
I don't know.
Anyone remember? What is a logarithm?
A lot.
It's the opposite of natural law.
Opposite of natural. It's the swirl.
Okay. This is key to making sense of the rest of the chapter today and the rest of the chapter. A logarithm is an exponent.
Oh,
If you understand that a logarithm is an exponent, it's going to make everything a lot easier. Okay, so for example, how do we read this? This is log base 3 of 52. Okay, so we say log base 3 of 52. 3 is called the base. 52 is called the argument. Right? Log base 3 of 52. And then we call 52 the argument. So if that's how we say it, how do we think of it? A log is an exponent. So we think of this as what exponent helps me change 3 into 52? And it's some decimal. But that's how we think of this. What exponent helps me change 3 into 52? 3 to what power equals 52? Again, a log is an exponent. So we want to know what exponent changes 3 into 52. So for example, here, write the logarithmic equation in exponential form. So what exponent helps me change 16 into 8? That would be 16 to the 3/4 power is what changes my base into the argument. Okay? Same thing here. Oh, actually not really. So ln means natural log of x, or we can read it as ln of x. So natural log of x is really log base e, and then our argument is e to the 3rd, and that equals 3. So e to what exponent changes e into e to the 3rd? 3, right? That's why it equals 3. So if we write this in exponential form, e to the 3rd power, my base to the 3rd power, equals my argument, which is e to the 3rd. Last year, we used the word swirl to help you remember. Okay, swirl means 16 raised to the 3/4 power equals 8. But again, if you understand what an exponent or what a logarithm is and that it's an exponent, you don't even have to memorize stuff like the swirl. If you're like, oh, what exponent changes 16 into 8? Well, the exponent is 3/4. So 16 to the 3/4 changes that into 8. Okay, so if you think about it, it's better to do that than to just be like, oh, swirl. Right? Well, what do we even mean? Like, what is swirl even doing for us? Okay. So same thing here. Write the exponential form in logarithmic form. Remember, the log is just the exponent, so we know that this is going to equal 3/2 because 3/2 is my exponent. So the log base 9 of 27. Right? So we wanted to know 9 to what exponent changes this into 27. And that would be 9 to the 3/2 power. Changes it to 27. Okay. Again, you can still think of this as a swirl. Log base 9 of 27 equals 3/2. So you can think of that. That's a good way to help you remember, but I want you guys to really be thinking, oh, well, the exponent's just the log, right? So the log equals the exponent. And we just wanted to know what exponent changed 9 into 27. All right, so write 1 over e to the 4th equals 0.0183 in logarithmic form. So I'm going to change this so that we don't have a fraction. So if I move this to the numerator, we have to make the exponent negative in order to move it. So that's really e to the negative 4th power. So again, you can think of this as swirl, but my exponent, right, it's going to equal my exponent, because that's what a log is. And we just wanted to know log base e to what power changes it into 0.0183. So again, you can think of this as swirling. Log base e of the decimal equals -4. But really think about what you're asking here. E to what power changes it into 0.0183, and that power was -4. So, like we just said on the last page, ln of x is called the natural logarithmic function. We can either say ln of x or the natural log of x. The natural log of x is equivalent to log base e. So what we're going to do here, log base e is really ln of x. So we're going to change that to ln of 0.0183 equals -4. So again, log base e is the natural log. Alright, so evaluate g of x when x equals 10,000. Well, evaluate just means to plug in. So we're going to plug in 10,000 for x. Remember, a log is just an exponent. 10 to what exponent changes it into 10,000? The fourth, right? 10 to the fourth is 10,000. So then y equals 4. Again, we're just asking ourselves, the base to what power is the argument? And that power would be the fourth power. Now, if you wanted to think of this as swirling, you could. G of x is really y, so you could swirl it and say 10 to what power equals 10,000? 10 to what power equals 10,000? Well, because there's 4 zeros, right, then it's going to be 10 to the fourth power, so y would equal 4. It's the same thing, we just didn't write it out, but we were asking ourselves the same question. 10 to what power is 10,000? Now use a calculator to evaluate the function at the indicated x value. Round to the nearest 1,000. Our calculator has one log button. The button says LOG. That means log base 10. Log base 10 is called the common log. Alright, so when we type this in, we're going to use that log button. So we'll plug in 4.3 for x. So we get 1.9. And then we use the log button, which is right here. Now it doesn't say base 10, but it's implied that it's base 10, because that's what the common log means. And then of 4.3. So nearest 1,000 would be 1.204. I just wrote it in function notation, but you could just write 1.204, and that would be fine. Properties of logarithms. The more you practice these and do these, the faster you start to see them, and you're like, oh, yep, got it. Okay? But you can always swirl to figure it out. You can always think about what's going on. It's just, when these happen often and you recognize them, it's just quicker to recognize the properties. So this property says that log base a, and then if you have an argument of 1, it's always going to equal 0. Why? Because a to the 0 power is always going to be 1. Right? So if you have an argument of 1, then you know it has to equal 0. You have to raise it to the 0 power to get 1. Log base a of a, so really this is just asking a to what power gets me a. And that's 1. A to what power gets me a to the x power? That would be x. Right? I have to raise a to the x power in order to get my argument of a to the x power. And then, same thing here. That's called the inverse property. Here, if you have log base a and log base a on both sides of the equation, then your arguments are equal. So then we know x equals y. And then we'll look at the properties of natural logarithms in a couple examples. So, we are solving the equation for x. All of these have equal signs. They're all equations, so we're going to solve the equations for x. So 5 to what power gives me 5? 1. Right? 5 to the first power gives me 5. Same thing here. 2 to what power gives me 2 to the negative first? That would be -1. And here, 4 to what power gives me 4 to the third? That would be the third power. Here, I have log base 6 on both sides, therefore my arguments are equal. X equals 8. 3 to what power gives me 3 to the fourth? That would be the fourth power. And then here we have log base 4 on both sides of the equation. So my arguments are equal. And instead of writing 7 to the negative first power, I'm going to change that into 1/7 equals x. Okay? So again, you're just asking yourself the base to what exponent equals the argument. Now, you could also think of this as canceling. Right here, a log base a of a, that's just 1. Right? That's the property. Same thing here. So we get -1 equals x. Same thing here. So we get 3 equals x. But that's because of what we just considered, right? There, so we get 4 equals x. So you can think of it either way. Now, if you had to swirl, you could even swirl. If you're like, I'm stuck, I don't know what the property is, what do I do? You can just say 5 to the x power equals 5. Well, this is 5 to the first. We have the same base, so then we know x equals 1. Okay, but using the properties is going to be easier. So now we're going to use the properties to simplify the expression. We're not solving because there's no equal sign. We're just simplifying because it's just an expression. So here, we can use the inverse property, right? So 6 to log base 6, then we just get 36x. There's two different ways that you can think about b. I thought of it as, so I just focused first on what exponent changes 2 into 1/2. -1. Yeah, exactly. So then we had 3 times -1, which is -3. You could also change, to begin with, you could change the 1/2 into a 2 to the negative first power. And then you get 3 times, right? And then we have -1, so we still get -3. I don't care which way you think of it. That part's up to you. But there's another way that you could have simplified that expression. Okay, so coming down, we have a couple additional problems. We have log base 2 on both sides. Therefore, my arguments are equal, so x equals 3. So 4 to what power is 4? The first power. Right, so that's just 1. And that was our second property here. It's just 1. 5 to what power is 5 to the x? X power. And then here, so those were equations. Here we just have expressions that we're simplifying. And then we have 14. And that's using the inverse property, which is the third one. Good luck. All right, we did graph logarithmic functions like this last year. So we get to pick which x values to plug in. So let's pick nice ones, and we're going to raise 4 to that power. So 4, we'll raise this to the, let's go negative first power, 4 to the 0, 4 to the first, and 4 to the second. Actually, 4 to the second is going to be off our graph, so we don't really need to do that one. So 4 to the negative first power means we're going to move that to the denominator, so that's just 1/4. 4 to the 0 power is just 1, and 4 to the first power is 4. All right, so let's plot those. -1 up 1/4, 0, 1, and 1/4. So there's f of x. So that was in exponential form, so it made it easy for us to graph. This is in logarithmic form, but we're going to change it to exponential form so that we can graph it. So how do we do that? Well, this is really just saying y, right? And so now let's swirl. We just want to know 4 to what power equals x, right? 4 to what power equals our argument, right? I have to raise 4 to what powers to change it to x. So, because the y is my input now, we're going to pick values to plug in for y. And look, it's very similar. So, let's pick the same values to plug in for y. So 4 to the negative first is 1/4, 4 to the 0 power is 1, and 4 to the first power is 4. So what do you guys notice about these two tables? Yeah, they're inverses. How do you know? Because the x and y are switched, right? That's what inverse means, the x and the y are switched. So yeah, these are going to be inverses of each other. So when we plot them, when we graph them, we should see symmetry over the line y equals x. That's what it means to be symmetric, that's what it means to be inverses of each other. You will see symmetry over the line y equals x, and we do. That's not an asymptote. Okay? It's just saying you can see the symmetry over this line y equals x. And that's because these are inverses of each other. Okay, here's two more functions that are inverses of each other. You can see the symmetry over the line y equals x. This is e to the x power, and this is ln of x. They are inverses of each other. ln of x and e of x, e raised to the x power, are inverses of each other. And you can see that reflected in the graph. Describe the transformation of the graph of f that yields a graph of g. No different than any other transformations we've been doing. So x plus 7, that's going to be a translation to the left 7. The negative is going to be a reflection in the x-axis. And the 3 is going to be a vertical stretch by 3. And then we have the -1 is a translation to the right 1. And +4 is up 4. Does it matter if we do 4 plus the log or the log plus 4? No, it doesn't matter what order you add in. So that's okay that the 4 is in front there. All right, and now we're going to do the same thing with properties of natural logarithms. So very similar. Ln of 1 is 0. So remember, ln is the same as log base e. So we're just saying e to what power is 1? And that would be e to the 0 power is 1. Okay, ln of e is 1. Again, really, this is just log base e of e. Right? So we're just saying e to what power is e? And that's why that's 1, because it's the first power. Right? E to the first power is e. Again, e, so this would be log base e of e to the x. So we're just saying e to what power is e to the x? And that's the x power. Right? So that's why that equals x. And then same thing, if you have natural log on both sides, then your arguments x and y are equal. Okay, so use properties of natural logarithms to rewrite the expression. So we know that ln of e is 1. That's property 2. So we know that part's 1. And then we have times the negative out front. So we just get -1. ln of e to the 0 power. So that's using the third property. And that's just 0. Right. Times 7 is 0. Right here, this is our inverse property, so that's 22. And here, I'm going to change this into e to the negative 4th, so that we don't have a fraction. And just like we did for b, this is just negative 4. If you want to think of it as ln of e as canceling, you can. They're not really canceling, because ln of e is just 1. Right, so you can kind of think of it like that if you want to. All right, this is the new part. So this is the stuff we did not do last year. All right, find the vertical asymptote and sketch a graph. So now we have some transformations going on here. So we're going to work backwards. Right? We are going to figure out what values of x can I plug in so that I have an argument where I will know what the exponent is. Right? Remember, log is just an exponent. So we want to get we want to pick very specific smart x values that when we plug them in, we're going to know 4 to what power is going to make it that argument. Okay, so we're going to work backwards in order to get those x values. Then at the end, once we plug in those x values, we'll have to eventually add 2 as well. But for now, we're going to figure out what x values do I need to plug in so that I can find that exponent. Okay? Yeah. We can do negative 2. So we're going to pick the exponent. So let me go through this first. So log base 4, I'm going to start with negative 1. We could do negative 2, okay, which is going to be really small. But 4 to the negative first power would give us 1/4. Log base 4 to the 0 power, 4 to the 0 power would give us 1. Log base 4 to the first power would give us 4. And log base 4 to the second power would give us 16. So, we just decided what our exponents are. We're done with that part, but we need to figure out what x values are going to give us those exponents. We don't know that yet, right? We don't know we need to figure out what x values do I need to plug in so that I get these exponents, right? That's what a log is. The log is the exponent. So, if I want an argument of 1/4, what would I have to plug in for x? So what we can do is set this equal to x plus 3 and solve for x. 1/4 minus 3 is negative 2.75. So if I plug in negative 2.75 for x here, then I get an argument of 1/4, and then I can actually answer the question. 4 to what power is 1/4? And I can say, oh, I know, that's negative 1. Right? I know what that answer is. Right? Again, let's do the same thing. What value of x am I going to have to plug in to make this argument 1? Make this argument 1. Okay, so we set this equal to x plus 3. Subtract the 3. 1 minus 3 is negative 2. So if I plug in a negative 2 for x, I get an argument of 1. And then I can say, oh, what exponent changes 4 into 1? That would be 0. And then we do it again. Subtract the 3. 4 minus 3 is 1. So again, if I were to plug in 1 for x, I get an argument of 4. So then I say 4 to what exponent gives me an argument of 4? That would be 1. And then one more time. So 16 minus 3 is 13. So again, if I plug in 13 here for x, I get 13 plus 3, which is 16. And then I ask myself, 4 to what power gives me an argument of 16? That would be the second power. So when we plug in x, we've already done this work, right? We've already done this work. We know that when I plug in negative 2.75, I'm going to get an exponent of negative 1. So the last part that I need to do now, right, because we've already plugged that in because we worked backwards, the last part we have to do is just add the 2. to get our y values. Okay? So we plugged in those x values, and we just have one last step is to add that 2. So we get 1, 2, 3, and 4. So let's plot these points. Actually, I didn't talk about the vertical asymptote. Your argument cannot be 0. We can never take the log of 0. Okay? That means this argument, x plus 3, whatever value makes that 0 is going to be where our vertical asymptote's at. So we take the argument, set it equal to 0, and that means we have a vertical asymptote at negative 3. Because if we were to plug in negative 3, we'd get an argument of 0, which we can't have. And then let's plot our points. Negative 2.75 up 1. Negative 2 up 2. 1 up 3. Make sure you guys go over to positive 1. Okay? Instead of just negative 1. So positive 1 up 3. And then 13, 4 is off my graph. So there's our logarithmic function. That's confirmation that we did it right because it's approaching my asymptote. So I'm like, yeah, that makes sense. We know we have the correct values then. Okay. So again, let me go through the process one more time. We picked our exponents and we worked backwards and we said, okay, well we want our exponents, right? Our logarithms, our exponents to be negative 1, 0, 1, and 2. So then my base would be 1/4, 1, 4, and 16. You're welcome. Good luck. And notice all of our arguments are powers of 4, right? 4 to the negative first. Sorry, 4 to the 0 power, 4 to the first power, 4 to the second power. Okay, our arguments are all powers of 4. And then we set our argument equal, right, so that we know what value of x we would have to plug in to make the argument that value, and then we actually plug x in. Although that work's done for us, so then we only had our last step supposed to. All right, one more. Let's do the vertical asymptote first. So we're going to take our argument, 2x plus 1, set it equal to 0, and that means there's a vertical asymptote at negative 1/2. That's not a very straight vertical asymptote, but let's just go with it. Okay, that's a little bit better. Not really. Okay, so vertical asymptote at negative 1/2. So now we have log base 2. So we are picking our exponents. Negative 1, 0, 1, and 2. Those are going to be the same every single time. So 2 to the negative first power would give us an argument of 1/2. 2 to the 0 power is an argument of 1. 2 to the first power is an argument of 2. And 2 to the second power is an argument of 4. I'm working backwards here. Okay? So now you can see 1/2, 1, 2, and 4. Those are all exponents of 2. So we have to figure out if I want my argument to be 1/2, if I want this whole thing to be 1/2, then what would I have to plug in for x? So 1/2 minus 1 is negative 1/2. Negative 1/2 divided by 2 is negative 1/4. And if you guys need to write out that work, you can. If you do in your head, that's fine as well. I'm fine either way. So let's do that again. What value of x do I need to plug in to make the argument 1? So 1 minus 1 is 0, divided by 2 is 0. So if I plug in 0 for x, I'm going to get an argument of 1. Right, 2 minus 1 is 1, divided by 2 is 1/2. And then 4 minus 1 is 3, divided by 2 is 3/2. So we were just choosing values of x to plug in so that we get a specific argument so that we can get our specific exponents. So that part's already done, right? If we plug in 0 for x, I get an argument of 1, so then I ask myself, 2 to what power is 0? And that would be, well, hang on, 2 to what power gives me an argument of 1? And that would be 0. So we already did this part, right? Here's my answers. Here's my exponents. So now my last part is this over here. We need to multiply by -3 first. You do not do 2 minus 3 here, because order of operations is multiplication first, then addition. This isn't a -3, it's a -3 times something. So we're going to multiply these by -3 first. And we get 3, 0, -3, and -6. And our last step is that we have to add 2. So +2, +2, +2, +2. And that gives me 5, 2, -1, and -4. Alright, so let's graph that. -1/4 up 5, that's really close to my asymptote, so that's a good sign. 0, 2, half -1, and 1/2 -4. So that's good confirmation that we did it right, because our function is approaching our asymptote.